Good afternoon, this is Mr. Schweitzer. We're doing a little review of some particular things on intermolecular bonding here. It says, use the back of the sheet of paper if need be. For covalent compounds, draw a simple Lewis structure, indicate areas that might be of interest and why. Okay, so in this case, two nonmetals, it would be I like this and Cl like that. You can put your dots on there to show that. Saying this guy is bigger than this one. Why is this one bigger? Only force we have here is London dispersion forces. No highly electronegative atom to draw electrons over. This guy is bigger because of more electrons, therefore it is more polarizable. Okay, that's the term they like. This one here, I have this guy, and it's kind of already drawn out here, versus saying this guy is smaller than, let's say, this guy. Okay, and at this point, there's an extra H here. There should be. Let's look like this in order to make them the same. Alright, this guy has hydrogen bonding. Partial negative, partial positive, and with hydrogen bond, some other thing that has any positives or negatives, likely itself. This one has more electrons, therefore has more London dispersion forces, but it's not enough to overtake that of the hydrogen bonding, and it's got a stealer here, but it's symmetrical, and that's important. Alright, this guy, similar here. We got C and C. This is number 3, I guess we're looking at, and then OH versus CH4. Okay. At this point, we got ourselves hydrogen bonding, partial negative, partial positive. Alright, this guy just has London dispersion forces. This guy here, number 4, we have carbon-carbon, just looking like that. And versus another guy. Once again, this is a situation where we have partial negative, partial positive, since we have ourselves a highly electronegative atom right here. This guy has hydrogen bonding. This guy has just London dispersion forces, and not really even all that much. Therefore, this guy is greater than this one as far as melting point is concerned. Alright, these guys, first one, we're talking ionic. Metal and non-metal, metal, non-metal. First we look at here for difference of melting point is positive 2 minus 1, positive 1 minus 1. Difference of charge. These guys are ionic. Positive 1. There's a little more room here. So I lost that. Looks a little weird, but looks like 6 got moved. Whatever. 2 ionic compounds. Look at our difference of charge, and try to erase some of this here. May not work. Either way, look at your charges. Looks like I get a positive 2 minus 1 on the calcium chloride. Sodium chloride is going to be simply positive 1 minus 1 in the chloride. And then just separate that. Now we're to SO2 and CCl4. I got SO2 looks like this, and has some unbonded pair of electrons here. This is number 7. So in this case we have a stealer and it's bent. Okay, so therefore this thing is going to have dipole dipole interactions, and the CCl4 is going to have essentially nothing. It is got chlorines all around. Therefore, it does have lots of London dispersion forces, especially because it has so many electrons. But this one is dipole-dipole. It's saying that this guy is above this one. In real life, I would also note just that sulfur dioxide happens to be a gas. It does in fact have this situation, and it does in fact have some dipole forces, but CCl4 in nature actually is a liquid. So we might say, well, we know that dipole-dipole generally are bigger than that of just a simple London dispersion forces. So a question might ask, why is this guy a liquid and this is gas? Well, it turns out that the sheer number of electrons is amplifying the London dispersion forces enough to exceed that of SO2. So regardless of what this thing says on here, I would say that this guy here in real life is the other way around. Water versus carbon dioxide. Okay, so we got, in this case, H2O versus CO2. Alright, water looks like this. These are all molecules. They're all covalent. We have ourselves a stealer right here, creating a partial negative and a partial positive. This guy can exhibit hydrogen bonding. This guy would like to do, hydrogen bonding, or any dipole-dipole, but it does have a partial negative, partial positive. Because we're linear, okay, this thing cancels, and we have no dipole-dipole, no hydrogen bonding. So the symmetry of this thing is important. We have London dispersion forces, which is why this thing is in fact a gas at room temperature. We have finally CH3, so 2 carbon chain and a 1 carbon chain. Okay, we'll do that one right here. Carbon versus carbon chain versus, let's say, a single carbon chain. Of course, at this point, they both have similar builds, everything the same, except for the fact that this slightly longer chain will allow for slightly elevated London dispersion forces. Explain why the following three systems vary so greatly in their melting points. Okay, we have, in this case, HF, which is a negative 83.6. I got water, which is at 0, and I got KCl, which is 770, and finally we have diamond. Okay. In this case, a couple things you want to just sort of rest on would be bond type. This guy is your network covalent. Now, again, it's just a clarifying point here. When you melt something, you kind of break something. You disturb something. What you break depends on how hard it is to break. So in this case, we're breaking a diamond. We're breaking a covalent bond, which is very strong energy-wise. This guy, you're breaking an ionic bond. These two guys here, technically they both would be breaking a hydrogen bond. And whether it's, like this, okay, or whether it's like this. All right, this is my partial negative, this is my partial positive, this is my molecule. We'd be breaking interactions between the molecules. All right, and we'll stop there. Thank you very much.